When you mix salt and water, the salt dissolves and forms something called the solution. That just means the salt spreads out so evenly in the water that you can't see it anymore, but trust me, it's still there. Solutions like this are all around us, not just in the ocean. The air we breathe, the drinks we enjoy, and even the fluids in our bodies are all examples of solutions. The world is basically built on them. Our bodies are made up of about 70% water, but it's more than just plain water. It's part of a solution that helps keep us alive and healthy. Solutions in our body allow important things like nutrients, oxygen, and medicine to travel wherever they're needed. Outside the body, solutions play a huge role in everyday life too, from helping doctors deliver drugs more safely and effectively to making it possible to clean and reuse water for communities around the world. Solutions are a simple idea, but they're a part of a big and how our bodies and our planet work. When salt or any substance mixes into water, it's not as simple as it looks. There's a lot happening at this tiny, invisible level. Scientists use something called models to help them understand and predict how this mixing or salvation really works. These models act like smart shortcuts using computer power to solve complex problems that would be too tricky to do by hand. The more detailed the model, the more computer time it needs. So it's all about finding the right balance. Choosing the right model helps us better understand solutions, which is super important because the liquid around substances can actually change how it behaves, looks, and how it even reacts. Models make it possible for scientists to explore all this without even stepping into a lab. One type of model is called the salvation model. These models help scientists understand what happens when something is dissolved in a liquid, like salt and water. Because the process is super tiny and very complex, it's almost impossible to figure it out by hand, so scientists use computers to do heavy lifting. These salvation models let us zoom in on the action and predict how things will behave in a solution, which helps in everything from designing new medicines to cleaning up water. A calm swimming pool, that's like a solution. Now toss in a floaty. We'll call that floaty a carbon atom. Then you toss in another floaty. This one is oxygen. And another, we'll toss in another oxygen floaty. When these floaties link up, they form dry ice, or in science terms, solid CO2. Once they're connected, the water in the pool can only get so close before hitting an invisible no-go zone around them, just like how you can't push a floaty past its black edge. This invisible barrier is called the cavity. But here's the cool part. In this research, the water wasn't even real. Scientists use a trick called implicit salvation, where the computer pretends the water is there without actually drawing every single water molecule. Now let's zoom in on one of those floaties, the carbon floaty. If you look closely, you'll see it covered in polka dots. These polka dots aren't just for decoration, they actually help the personal space around the floaty, telling the water how close it's allowed to get. In science, we call this the salvation radii, but you can think of it as the bubble each floaty creates in the pool. If you change the size of the polka dots, you can change how far the water can swim up to the floaty. Bigger dots mean more space, smaller dots mean the water can sneak in closer. In this research, these polka dots will be the real stars of the show because adjusting them will help us understand how the floaty or the solute in the water, even when the water isn't real. Or pool. Scientists have a few default ways to choose the size of those polka dots on the floaties. Some of the most common ones are called UFF, Pauling, and Bondi. These work okay as a starting point, but the problem is they only think about the floaty by itself, not what happens when the floaty is in water. That's why this research focused on finding better ways to size and place these polka dots. The big goal of this research is to completely update those old one-size-fits-all polka dots or salvation radii and create new, more accurate polka dots for better salvation models. Why? Because the current ones just don't cut it. They can't capture all the details of how a floaty interacts with the water. There have been some important steps along this journey. Haskin worked on narrowing down the polka dot sizes for hydrogen, carbon, and oxygen, and Risbig did the same for nitrogen. Using those more accurate ranges, I'm adding phosphorus and sulfur to the mix. These are the next most common atoms we find in everyday life, and by including them, we're getting closer to that big goal of creating better models for solutions. This part of the research, we're going to use a total of 635 floaties or solutes to figure out the best polka dot sizes or salvation radii for phosphorus and sulfur. Started looking for the best polka dot sizes for phosphorus and sulfur, there wasn't a clear starting point because no one had studied them before. To help guide our search, we looked at something called periodic trends, which is just fancy of saying how atoms change as you move across the periodic table. When looking at the periodic table, you can see from left to right the electrochemistry increases, so we knew that sulfur was going to be a little bit more electronegative, but we also see that the size decreases, so we knew that sulfur was going to ultimately be smaller than phosphorus. Going from top to bottom, we see that the electrochemistry decreases, but also the size increases, so we knew that phosphorus and sulfur were ultimately going to be bigger than nitrogen and oxygen. As we started our search for the best polka dot size for phosphorus and sulfur, we quickly realized the search range was huge. With so many possible combinations, the total number of possibilities was way more than we could ever handle in the time given. To make the search more manageable, we decided to narrow it down. Instead of looking at all 180 of those possibilities, we focused on a smaller, more manageable subset, just 70 solutes that contain phosphorus and sulfur. This smaller group still gave us a good range to work with and ultimately led to a doable number of combinations. The goal of this research is to create new polka dot sizes for phosphorus and sulfur that are more accurate and can be used for future research. By refining these sizes and narrowing down the ranges, we'll make it easier and quicker for the next future research. Once the computer finished testing all the different polka dot sizes for phosphorus and sulfur, it gave us three important types of results: errors, failures, and hits. The error was just the computer's way of seeing how far the polka dot size was off from being the perfect fit. If the polka dot was doing really, really bad, you were considered a failure. And if you were doing outstanding, you were a hit. For this research, we decided that any error between plus or minus 1 was totally acceptable. You'll see this clearly marked with yellow highlights in the results slides. Let's talk about how we figured out the best polka dot size for sulfur floaties when they were floating in the pool all by themselves, just neutral. When we found the polka dots were set at about 2.0, the computer gave us really good balance. When we also tried a slightly smaller polka dot size at 1.9, the fit was still pretty good. So we found the sweet spot for sulfur's polka dot to be around 1.9 to 2.1, as going down to 1.8 produced pretty inaccurate results. Now let's switch gears and talk about the charged sulfur floaties. These are the ones that aren't neutral but carry a little extra electrical push or pull, or kind of like the floaties with a little built-in magnet. What we found was pretty interesting. The best fit for these charged sulfur floaties showed up when the polka dot size was around 1.8. At this size, the floaties seemed to fit just right in the water, not too tight, not too close. Now let's dive into the last part of this research, the phosphorus floaties. Compared to all the other floaties in the pool, phosphorus didn't show up very often. Out of the 70 total floaties tested, only 18 actually had phosphorus on them. One possible reason is that phosphorus floaties like to hide. Instead of hanging out on the edges of the floaty group where the water can really press up against them, phosphorus tends to tuck itself away safely in the middle, surrounded by its other atom friends. When we were looking at trends and we zoomed in, we noticed that the polka dots were on the larger side, around 2.1 to 2.2. The fit was the best. There were fewer problems and more floaties matched the way we wanted. So even though phosphorus was a bit shy and didn't like to hang out on the edge of the group, when it did show up, a larger polka dot size gave the best results. Results, the proposed polka dot sizes for phosphorus was 2.0 to 2.3 and sulfur was 1.8 to 2.1. Brings us to what's next. This project focused on a smaller group, 70 floaties that either had phosphorus or sulfur. But floating out there are still 635 total floaties waiting for their turn. The exciting part? Now that we've narrowed down the sweet spot sizes for phosphorus and sulfur floaties, future testing will be way faster and way easier. At the start, we had 6 different polka dot sizes for each floaty. Now we've turned it down to just 4 sizes. In the end, this research is all about fine-tuning the personal space of each floaty in the pool. And now we're one step closer to building a model that's smoother, smarter, and faster for future science.